Alright, we left off last chapter talking about the slope of a function at just one point, where x equals a, and it had to have a limit because if you do f of a plus h minus f of a, that's the change in the y values, and then divided by the change in the x values, which becomes h, you have to scooch those points closer together, so that's why we include the limit as h approaches 0. This whole thing is a limit, and when this limit does exist, it's called a derivative. And if f prime of x exists everywhere, we say that f is differentiable. If it's differentiable at every point within its domain, then the function itself is called a differentiable function. Now there's another way to talk about the derivative at one point at x equals a. This is just an alternate definition. You'll see this. It's actually not much different than the other formula for derivative. So you're going to see here, we've got the limit as x approaches a this time though. And we've got f of x minus f of a all over x minus a. So this is just another way to find the slope at one coordinate point. So let's compare the two of them and figure out the similarities and the differences within the two. And my cat just jumped next to me, and I hope he doesn't knock me over here. Alright, if we take a look at, let's just talk about a random curve, okay, for both of these guys. This would be f of x, and this is going to be x. This would be f of x, and this would be x. Okay, for both of these guys, if you're talking about a point at x equals a, okay, in order to get that tangent line or the derivative at that coordinate point, we're going to pick another point arbitrarily close. For the formal definition, we said we were going to move over an amount, and we were going to call that amount h. So this would be the x value of a plus h. Now on the alternate definition, we're just going to say this is just going to be another x location, so we'll call it x. Okay. In either definition, a is the coordinate point that we do have. A is a known value, and if we move up to the function here, this would get us that secant slope. Okay, so in order for this to become a tangent line for the formal definition, we said we were going to take the h value and we were going to squish these two coordinate points closer together by making h approach 0. So that's what where this comes from. We've got f of a plus h minus f of a, that's the change of y, all divided by h, so that's the change of x, and we were taking that as h approaches 0. So this alternate definition comes in and says if you take another point, you just randomly call it x, and you connect those 2 points, this would be f of x minus f of a. So there's your change of y again, and this time the change of x is just going to be x minus a. And again, we want to make the change of x go towards 0. So here we're not defining h as a distance between the two of them. So in order to make this limit, in order to make these two coordinate points approach each other, you would just have to slide x closer to a. That's why in this definition x is approaching a. One of the most confusing parts about this entire chapter is just knowing what to do with the given directions. So if your directions ask you to do any of these 4 things, it just means to find the derivative. If you're asked to find the slope of the tangent line, the slope of the function, the instantaneous rate of change, or when they ask you to differentiate, it all just means the same thing. And you can choose either method that you find easier to work with. But I'm going to show you both of them in example 1 when it says differentiate f of x equals rad of x. The formal definition of derivative, you'll notice that it didn't give you a starting x value, so you're just going to use f of x plus h instead of f of a plus h minus f of x all over h. One of the things that I notice a lot of people getting tripped up on is getting to the point where you talk about f of x plus h. Remember, that just means anywhere you saw an x in your original function, you now substitute in the x plus h. We haven't taken the limit yet. We can't, because if we plug in and substitute h is 0, we'll get a 0 in the denominator. So f of x plus h becomes the radical of x plus h. F of x was just radical x, and this is all divided by h. And hopefully you are thinking to use the conjugate right now, and that would be appropriate. So here's my original, and I'm going to multiply numerator and denominator by the conjugate. The sign underneath the radicals don't change, it's just the signs between the radicals. Clever form of 1 here. Can't change the value of the fraction, so we're just going to multiply by the conjugate. We have not taken the limit yet, so we're going to keep the limit as h approaches 0 in there. And if you FOIL the numerator, you're just going to get x plus h. The minus and the plus from each term are going to go away, and then you're going to have minus x. And this is all going to be over h times the quantity of rad of x plus h plus rad x. Notice I didn't distribute on that quantity, because in the numerator you are going to get the x's to cancel out, and you've got the limit as h approaches 0 of h all divided by h rad of x plus h plus rad of x. Now we are able to cancel the h's, which is going to eliminate that 0 in the denominator. Now we can substitute, and when we substitute, we no longer need the limit notation. Plug in h is 0 and you get rad of x plus another rad of x. That gives you 1 all over 2 rad x. So using the formal definition, this is the derivative. It is actually an equation that is going to give us the values of the slope for any value of x. Okay, and obviously I had to write a little bit big, so I'm going to see if I can squeeze in part B here, and if not, I'm just going to have to erase a little bit of what I did for part B, and I'll try to write small, but still big enough that you can see it. The alternate definition of the derivative says to take the limit as x approaches a of f of x minus f of a all over x minus a. And f of x is just rad of x. F of a is just radical a all over x minus a. Again, we would try to substitute x equals a in here. We can't, we get a 0 in the denominator. And again, you're just going to use the conjugate. We haven't substituted anything yet, so again, we're going to keep the limit notation. And if we do that this time, we're going to have x minus a all over the quantity x minus a times rad x plus rad a. Sorry for squishing that in there. And you will notice that the numerator and denominator cancel just like we knew they would. And you're going to have the limit as x approaches a of 1 divided by the rad of x plus the rad of a. Now we can substitute, and we get 1 over 2 rad a. Okay, so this would give us the slope for any x equals a. Notice it's the same as what we got before. It's just a personal choice on whether you like whichever definition you like. Okay, so there's a lot of notation to talk about the derivative. Whether it was Newton or Leibniz, they all came up with their own interesting ways to talk about the derivative. You should be comfortable using any of the notations that I'm about to show you. So first of all, f prime of x was one way to talk about the derivative. Another way is y prime of x. Another way is just y prime. You can also use dy dx, which I believe we used last chapter. You can also use d dx of f of x. And you can also use df dx. All of those things mean the same thing. It means the derivative. I think that the most useful ones are this one right here, this one right here, pretty much anything that tells you, what you're taking the derivative with respect to. So this is the derivative of y with respect to x. This is derivative of the function f with respect to x. So it's very clear on what your independent and dependent variables are. So last example that we have, it's asking us to find the lines that are tangent and normal to a function at x equals -3. If g of -3 equals 1 and g prime of -3 equals 1/2, when you see the word tangent, again, hopefully you're thinking derivative. This is a pretty straightforward problem, as long as you are aware that in order to come up with an equation for a tangent line, you just need a slope and you need a point. And here's our point right here. This is -3, 1 is a coordinate point. And then our slope is actually over here because this is the slope at -3, at x equals -3. So this is like your m value. So for the tangent line equation, you're just going to use your point slope form. Y minus 1 equals 1/2 times the quantity of x plus 3. Now, one of the reasons why it's so useful to leave it in point slope form is because then you can just jump right to your normal equation. You're going to have the same x and y coordinates that you used for the tangent line, and the only difference now is that the the opposite reciprocal slope is used for the normal lines, because again, normal and tangent are perpendicular to one another. And that's it. So if you have any questions, make sure you ask me tomorrow.